Today I'd like to take a few moments to review with you the ideas we learned about capacitors last year. So we've already gone through and talked about circuits that have resistors. We saw how the battery pushes the charges through the resistor. The charges are going to generate heat as they move through the resistor and then go back to the other side of the battery. Capacitors are totally different. So I want to remind you of the 4 different kinds of capacitors that you might run across. There's actually many more, but these are the 4 most common ones. Okay, so sometimes you'll see big guys like this. Sometimes they'll look a little smaller like that. You'll see ones that kind of look like little chiclets and ones that look like little hamburgers. Regardless of what the capacitor looks like, inside it will be composed of a few parts. You will have a metal plate, and in between the 2 metal plates will be an insulator. In this case, it happens to be air. Okay, so this is what our capacitor is looking like. We have it hooked up to a battery, and what I'd like you to trace out is how this capacitor actually works and what its function is. All right? So the charges are going to come out of the negative, they're going to flow through the wire, and they're going to start to build up on this negative plate. The problem is negatives repel each other. So the negatives on this plate are going to try to prevent more negatives from coming off the battery and going onto that plate. However, on this plate, we have something else going on. The negatives here will repel the negatives from this plate onto the positive of the battery. This will leave behind positive charges. These positive charges help to pull more negatives onto this first plate. Yes, they're still being repelled by the negatives that are there, but these positives will help a little bit to overcome that, and we will get a few more negatives stored on that plate, which will then push a few more negatives off of this plate, and eventually we'll reach a point where we can get no more negatives onto our first plate and push no more negatives off of the second plate. At that point, the capacitor is fully charged for that battery. So this battery happens to be 6 volts. And that capacitor will only be able to hold a certain amount of charge when hooked to 6 volts. If we used a bigger battery, it would have more push and would be able to put more electrons onto that plate. The charge that is stored on the capacitor is equal to the capacitance, which we'll figure out again. We had it last year, how to find that, multiplied by the voltage of the battery. I want to make sure you realize when we say the charge of the capacitor, we're talking about the charge on one plate, because the capacitor is still neutral. It's got 1 positive plate and 1 negative plate, so the net charge is still 0. So when we calculate charge, we're calculating how much negative charge is stored on one of the plates. Okay, so there are 3 factors that affect how much charge we can push onto the capacitor with a given voltage. Okay, so one of those is the plate area. That's going to go by the letter A, and it's going to be in meters squared. The more area there is, the more space there is, the more electrons we can put on our plate. Remember, these electrons are going to be repelling each other, so they're going to want to get as far away from each other as they can. So if we give more area, we'll be able to get more electrons onto that plate. The second factor is separation. That goes by the letter D. Again, this plate will have an induced positive charge when hooked up to a battery or other kind of circuit. And the closer we make these plates, the more effect that these positives can have in pulling more negatives onto the top plate. This separation is measured in meters. The third factor that affects the capacitance is the type of insulator in between. We'll see in a little while why that makes a difference. Okay, so for now, our formula looks like this. Capacitance, that's measured in farads. Most times the capacitance will be pretty small, so when we look back at our capacitors, we can see that these are microfarads. Sometimes you will even have nanofarads or picofarads. The capacitances are very rarely going to be whole farads worth of capacitance. Okay, so again, our factors were type of insulator, universal constant, area, and distance between the plates. These constants for the insulators can be found on your reference sheet. It's called the dielectric constant. With air, the value is 1, and the better the insulator, the higher that number will be. Okay, the EO, 8.85 e to the negative 12th. Area, again, is in meters squared, and distance between the plates is in meters. Again, the capacitor will not hold anything until we hook it to a battery or hook it into a circuit. Okay, and again, when this happens, we are going to have the electrons flowing onto the top plate, pushing electrons off of the bottom plate, gives us one plate negative, one plate positive. You can see when I make the plate area bigger, the capacitance goes up. You can see that when I make the separation smaller, the capacitance goes up. And we talked about why. A bigger area is more places to put electrons, and a closer distance means these positives can pull more electrons onto the top plate. The insulator is the tricky one. So if you look at the insulator now, you'll see that there are molecules that are polarized. They have a plus and a minus to them. And what happens is when you charge up the top plate, these molecules are going to align themselves so the pluses are attracted to the minus. And in effect, what you have done is you've brought the positive charge closer to the top plate, which allows it to have more effect of pulling electrons onto that top plate. Okay, so watch. You can see that the molecules start out not really separated, but you'll see as they get put into the capacitor, the positive end of the molecule tends to align itself with the negative plate. The negative end aligns with the positive plate, and in essence, you've brought the charges closer to the plates without actually changing the separation between the plates. Okay, so once we have the capacitance, to get the charge on the plates, we simply multiply by the voltage of the battery. To get the energy on the capacitor, we use a formula that looks like this. And again, we had these all last year. I'm just reminding you of what they look like. Okay, so your normal procedure is step 1, find the capacitance based on the object when it's not hooked up to anything. Then you hook it to your battery. You can then find your charge. You can find your energy. And finally, you can find out how strong the field is between the two. So if you look, we haven't really focused on it yet. When we charge up these plates, there's going to be an electric field generated between those plates. And you can see the field points from the positive to the negative, just like electric fields are supposed to point. And that is your final step to figure out how strong the field is between those plates. You take the voltage of the battery and you divide by the distance between the plates. Okay, so that is the fourth and final thing you can calculate. So that's just a quick refresher on capacitors. We're going to take them a little bit farther starting tomorrow.